For many decades, legions of scientists have attempted to reconcile the quantum mechanics of Heisenberg with the general relativity of Einstein. However, to date, no attempted solution is widely accepted as having achieved reconciliation. In this episode, we utilize the electrogravity-magnetic construct to integrate quantum mechanics with general relativity, or more precisely, we integrate the quantum vacuum with general relativity. This has already been achieved throughout previous episodes, however in this instance, we shall express the solution in compact tensor form. So, let's get started. The obvious question to begin with is, why has the integration of quantum mechanics with general relativity been so problematic? Well, to answer this question, let's consider what general relativity is fundamentally about, in its simplest conceptual terms. General relativity was developed by considering the pathways of light through gravitational fields, as shown by the illustration on the left-hand side. Hence, at the most basic level of comprehension, when we apply general relativity, we're applying it through a three-dimensional volume of spacetime. This volume is termed a manifold. So, try to remember, general relativity deals with volumes. This is an essential piece of understanding. What it tells us is that, from the perspective of general relativity, a single point in three-dimensional space-time, in isolation, is pretty much meaningless. For general relativity to be sensible, we need to speak in terms of volumes of space-time. However, in terms of the quantum vacuum, volumes are meaningless, only a single point in space-time makes any real sense. Thus, integrating a volume with a single point is obviously problematic. Let's take a look at how this impasse can be overcome. Let's begin by referring to a slide from episode 3, whereby we articulated that an important feature to summarize prior to moving forward is the refractive index, that is, what is it and what does it mean? To best answer these questions, we firstly need to consider general relativity. Appearing on screen is the historically famous solution developed by Albert Einstein, in compact tensor form. General relativity describes how space-time is curved by the presence of matter. We term this curvature as being a manifold, hence the expression space-time manifold. On the right-hand side of the illustration, you see a two-dimensional representation of how light from a star transits a space-time manifold to arrive at instrumentation on the Earth. Light from the star continuously travels in a straight line, but the path it travels is curved. This is possibly the best example to demonstrate how general relativity works and the value it brings to physics. However, general relativity does have some weaknesses. Firstly, it takes years to master and is profoundly limited. It says nothing about the mechanism for matter to curve spacetime and does not in any way explain why, precisely why, matter curves spacetime. Secondly, general relativity is built to operate across a volume of spacetime in order to map pathways of light. General relativity is a cumbersome tool when considering a single, specific, mathematical point in a spacetime manifold. Hence, a more convenient representation is desired. The polarizable vacuum approach to general relativity solves this problem by the utilization of the refractive index. The refractive index describes what's happening in the space-time manifold, but at a single point. It does this conveniently and succinctly utilizing the value of refractive index. The reason this single-point representation of general relativity is important and valuable is because, mathematically interacting with the quantum vacuum in order to unify general relativity with quantum mechanics, by necessity, requires a single point. Hence, the unification of general relativity with quantum mechanics at a single point can be readily expanded to a space-time manifold. Therefore, the method of single-point analysis reduces complexity and suits the refractive index of the polarizable vacuum approach to general relativity perfectly. Let's now take a closer look at the quantum vacuum. From episode 6, we learned that before we can address what happens to the quantum vacuum in the presence of matter, we need to understand the nature of the quantum vacuum ground state. That is, the quantum vacuum at its lowest possible energy level. In terms of general relativity, the quantum vacuum ground state denotes a perfectly flat space-time manifold. In other words, the quantum vacuum ground state is representative of Minkowski spacetime. The name given to this quantum vacuum condition is zero-point field. For many decades, vibrant debate has questioned whether or not the zero-point field is representative of virtual or real photons. Quantum electrodynamics favors virtual photons, whilst stochastic electrodynamics favors real photons. However, the electrogravimetric construct offers somewhat of a middle ground. The electrogravimetric concept of the zero-point field defines it to be a dark reservoir of quantum potential energy. This means that the zero-point field of flat spacetime cannot contain infinite real energy, but it does contain a vast reservoir of potential energy. This is extremely important, so please keep this in mind at all times. Because we consider the zero-point field to be a dark reservoir of quantum potential energy, it has no observable physical structure. Hence, we are required to assign a mathematical structure to it, in order to describe it. To be consistent with previous episodes, we shall describe the zero-point field as possessing the spectral characteristics of a Fourier distribution. However, in this situation, the amplitude spectrum denotes the probability of photons emerging randomly from the zero-point field. We'll discuss this in greater detail on the preceding slide, but for now, we can simply model the zero-point field by multiplying the unit harmonic operator by 0. Please refer to episode 2 for more information. In the absence of matter, that is, in a completely flat space-time manifold, the zero-point field exists as an infinitely broad spectrum of potential photon frequencies, randomly manifesting as real photons, then collapsing back into the zero-point field as quickly as they arise. This means that the harmonic cutoff mode and frequency associated with the zero-point field tends to infinity. This does not mean that an infinite quantity of real energy exists. It simply means that the zero-point field possesses the potential to release it, much like a battery. The process of energy release is random and governed by probabilities. However, it should be emphatically stressed that a truly flat space-time manifold does not and cannot physically exist. Special relativity and Minkowski spacetime are non-physical mathematical contrivances. Hence, it is statistically extremely unlikely that the zero-point field will release all of its potential energy in one catastrophic event. Let's now take a look at what happens to the quantum vacuum when we superimpose matter onto the zero-point field. In this illustration, we see the zero-point field modeled as a randomized spectrum of real photons. This is the effervescent baseline of the quantum vacuum driving the Casimir effect. But where does the energy for these wavefunctions come from? If the energy for these wavefunctions existed at the level of the zero-point field constantly, then all the energy within the zero-point field would be released in one catastrophic event. Therefore, a layer of reality must exist beneath the zero-point field where the energy for these wavefunctions must be stored. This is why we describe the zero-point field as a dark reservoir of quantum potential energy. In order for virtual photons to pop into existence, they must have been stored in some inaccessible layer of reality, as potential energy. Due to the storage layer for this quantum potential energy being physically inaccessible, we may imbue it with any structural format we wish. All logical formats are equally valid as they cannot be directly experimentally confirmed. Please do not confuse or associate this statement with the Casimir effect, which is experimentally observable. The Casimir effect occurs in the real world, but the dark reservoir of quantum potential energy fueling the Casimir effect is physically inaccessible. Therefore, it logically follows that any structural format applied to describe this dark reservoir of quantum potential energy should be efficient, in order to be consistent with all other natural phenomena. Hence, a very efficient way of storing quantum potential energy, mathematically speaking, is in accordance with a Fourier distribution. In the bottom left-hand corner of this illustration, we see the quantum potential energy associated with the zero-point field. The zero-point field is the physical manifestation of the quantum potential energy released into the physical universe when the quantum vacuum is in its ground state. We manifestly observe this process in the Casimir effect. The illustration depicts the amplitude and frequency spectra associated with the available quantum potential energy, formatted in accordance with a Fourier distribution, as described by the unit harmonic operator in episode 2. Each wave function denotes a population of virtual photons and exists in conjugate pairs, as indicated and required for net zero gain, hence the term 0 point. These wave functions mean that at any instant in time, populations of virtual photons pop into existence, but so do an equivalent population of virtual photons, 180 degrees out of phase. Consequently, no electromagnetic radiation is ever experimentally observed, mysteriously appearing from nowhere. So how do we interpret these curves? That's a good question, I'm glad you asked. The amplitude of each wave function denotes the probability of a population of photons popping into existence. As you can see, the probability of emergence into reality is significantly greater at lower frequencies than it is at higher frequencies. That is, the higher up the frequency spectrum we look, the lower the probability of virtual photons popping into existence. And as we have already established, for perfectly flat space-time geometry, the harmonic cutoff frequency tends to infinity. This also means that its probability amplitude tends to 0. In other words, it is impossible for photons of infinite frequency to exist in the physical universe. Hence, the universe cannot catastrophically collapse. When we add matter to the zero-point field, a major change occurs. The quantum vacuum becomes polarized by the presence of matter and compresses the frequency range of the zero-point field. The lower spectral frequency limit is upshifted from 0 Hz, and the upper spectral limit is downshifted from infinity. Both alternate spectral limits are mass-energy dependent. However, the structural format of the Fourier distribution is preserved. In other words, the mathematical description doesn't change, the Fourier distribution is preserved, but its lower and upper frequency limits have been modified, due to the addition of matter. We call this polarized form of the quantum vacuum, the polarizable vacuum. Thus, if we consider any mass to be represented by a point particle, we are in fact insisting that all of its mass energy is contained in the quantum vacuum field surrounding it. Therefore, if the quantum vacuum surrounding any mass can be described by a fully quantized Fourier distribution, as we have discussed at length throughout numerous episodes on this channel, then it logically follows that general relativity has been successfully integrated with quantum mechanics. That is, the missing link between general relativity and quantum mechanics has been established. Hence, the only remaining missing pieces of information we need are the spectral frequency limits of the quantum vacuum in the presence of mass. As it turns out, we have already derived the required limits in episode 4, so, let's take a look. In episode 3, we established the quantum vacuum amplitude spectrum, the quantum vacuum frequency spectrum, the refractive index of the polarizable vacuum and the fundamental quantum vacuum frequency. In episode 4, we established the harmonic cutoff function, the harmonic cutoff mode and the harmonic cutoff frequency. With both sets of derivation in place, we have a complete solution. We now have the ability to completely define all relevant and important aspects of the polarized form of the quantum vacuum, at position r, induced by gravitational mass m. Okay, let's now pull everything together. So, what does the final solution look like? The term we give to it is quantum integrated general relativity. We take the standard form of general relativity, and we introduce two modifications. One of the modifications introduced expresses the cosmological constant in the cosmological time domain, whilst the other modification introduced is termed the unit harmonic operator. The unit harmonic operator is simply the number 1, quantized harmonically over the Fourier domain. The fully quantized quantum vacuum spectral limits may be calculated utilizing the equations shown on the previous slide. The obvious question now becomes, how can we test our final solution? Well, testing the final solution involves two parts, that is, testing the standard form of general relativity, and testing our integrated modifications. Fortunately, the standard form of general relativity has been experimentally verified by mainstream science for over a century, so we don't need to address it herein. So, that leaves our integrated modifications. How can we test these? Well, fortunately once again, we've already tested these modifications extensively through the episodes on this channel. Let's take a look at the evidence. Experimentally verified evidence supporting our quantum integrated general relativity solution, is based upon one single equation derived from a process spanning episode 1 to episode 5. This single equation, appearing on screen as the second simplified harmonic cutoff frequency, is a precipitation, that is, a simplification, of the equation set appearing on slide 6. In this illustration, we see that our primary equation, which was derived in episode 1 to episode 5, yields astonishing experimentally verified results. We have confirmed that a single equation can be utilized to describe reality from the quantum scale to the cosmological scale, and everything in between. Everything on screen is significant and jumps substantially ahead of the standard models of particle physics and cosmology. But perhaps most notably, this 2008 power spectrum Hubble constant was predicted 5 years in advance of experimental validation. This is historically verifiable fact, and we suggest that you follow the links shown in order to verify it for yourselves. Now that we have established the scientific credibility of our quantum integration modifications, let's look at the governing physical principle. Our quantum integrated general relativity solution is constructed from a governing principle termed zero-point field equilibrium. This is a form of equilibrium whereby the zero-point field, that is, the ground state of the quantum vacuum, pushes back upon matter, acting to contain it. It's a knife-edge balancing act, whereby all matter exists in slight disequilibrium, by losing mass energy to the quantum vacuum. The quantum vacuum returns this energy in the form of virtual photons, as we see in the Casimir effect, ensuring a net cosmological equilibrated state, and ensuring that the mass-energy conservation law is satisfied. This principle has yielded the size of all fundamental particles, the Hubble constant and the cosmic microwave background radiation temperature. We encourage our viewers to review episodes 1 to 13. Let's now summarize what we have learned. On our journey through this episode, we have seen how it's possible to integrate quantum mechanics with general relativity, by including two modifications. The first modification is simply the cosmological constant expressed in the cosmological time domain. This is not a quantum mechanics-related modification, it is purely cosmological. However, our introduction of the unit harmonic operator relates the standard form of general relativity directly with quantum mechanics, that is, specifically with the quantum vacuum. It is essential to understand that the unit harmonic operator is simply the number 1, which has been decomposed and is fully quantized over the Fourier domain. Quantum vacuum spectral characteristics associated with the unit harmonic operator are given on slide 6, but a simplified representation of the high-end quantum vacuum frequency cutoff appears on the right-hand side of this screen. We have also identified numerous particle physics and cosmology examples, demonstrating the experimental validation of our electrogravity-magnetic construct. For viewers wishing to consult publications relevant to quantum integrated general relativity, you may do so by reviewing the episodes shown.